Section 12.5 Triple Integrals, Video 2. In the previous rather long video, I kind of showed you the natural extension from a single integral to a double integral to a triple integral. As we move up to triple integrals, we won't always be able to sketch the graph of the function that we're integrating. For example, if we graphed w equals xyz squared, we would need a four-dimensional graph in which to draw that because we have four variables working together. However, we can sketch a picture of the region, solid, over which we're integrating. In this case, we're evaluating the triple integral over the solid b defined over there of xyz squared dv, where b is the box defined by all points such that x is between 0 and 1, y is between -1 and 2, z is between 0 and 3. This would be a relatively easy picture to sketch. We would just need a x, y, and z axis. We're integrating between x equals 0 and 1, between y equals -1 and 2, and between z equals 0 and 3. So we would just need to locate the 8 corners of the box. If we use the least values for each coordinate, we have 0, -1, and 0. So 0, -1, 0 is back here. If we use the greatest values, we have 1, 2, and 3. So 1, 2, and 3 is about here. And then we can just find all the corners by choosing every possible pairs of x, y's, and z's. So 0, -1, 0, 0, -1, 3. So 0, -1, and then a 3. And then we'll take that one off for a second. And now let's do the 0, 2's. 0, 2, 0, which is here. 0, 2, 3, which is there. So these are the backs, the four corners of the back of the box, because I have the x that's furthest back. So let's go ahead and connect those. And then for the front of the box, we would have to go out to x equals 1. So let's pick up all those order pairs. 1, -1, 0. 1, -1, 0 would be about there. And honestly, I don't need to do the rest of them. If this represents the vector from the back bottom left corner to the front bottom left corner, then it would be the same vector for all of them since it's just a rectangle. And so there's a picture of the solid that we're integrating over. Do we have to draw that in this problem? No, because it's just a box. Our limits of integration are given to us. So how would we evaluate this? As a triple iterated integral. So the triple integral over that solid of xyz squared dv is equal to the triple iterated integral of xyz squared. And now I have to break the dv down into dx, dy, and dz, and the order actually doesn't matter. Because this is a box. In other problems, the order of integration will be super important. But let's just go with the natural one, which would be dx, dy, dz. So if we're going to integrate with respect to x first, then our first limits of integration are 0 to 1. And then integrate with respect to y, so our second limits of integration are -1 to 2. And then with respect to z, so our third limits of integration are 0 to 3. You can do like I did in the videos for the section over double integrals and polar coordinates, and export the first integral, evaluate it, and then import it back into the remaining integrals. So if we integrated from 0 to 1, xyz squared dx, the y and the z are being held constant, so we just integrate the x. The integral of x is 1/2 x squared. The y and the z squared are constant. We're evaluating from x equals 0 to x equals 1. I personally think it's important to write x equals on both of these limits of integration. Before we integrated, we knew they were x values because we're integrating with respect to x. But if I just write 1 and 0 over here, I have no evidence which variable those values are going to get substituted for. So it's good practice when you're doing double integrals, triple integrals, and beyond, when you're evaluating limits of integration, to specifically say which variable you're substituting them for. So if we substitute 1, that's easy, 1/2 yz squared. And if we substitute 0, the whole thing zeroes out, so it's gone. So subtracting 0 is nothing, so we're left with that as the value of the first iterated integral. So let's import that back into the remaining iterated integrals from 0 to 1, from -1 to 2 of this guy, 1/2 yz squared dy dz. And let's do it again. This time, let's export the inner integral, which is a dy integral, and do it separately. So the integral from -1 to 2 of 1/2 yz squared dy. The z squared is a constant, so we just integrate the y. The integral of y is 1/2 y squared, so we'll pick up another 1/2. 1/2 times 1/2 is 1/4. Y squared, z squared. And this is being evaluated from y equals -1 to y equals 2. So I'll actually have to substitute both of them. If I substitute the 2 squared is 4. 1/4 times 4 is 1, so we just have 1z squared minus, and if I substitute -1 for y, -1 squared is 1. 1/4 times 1 is 1/4, so we have 1/4 z squared. Z squared minus 1/4 z squared is 3/4 z squared. So there's the value of the second integral. So let's import that back into the remaining integral. The integral of 3/4 z squared dz. Now it's just a baby calculus 1 problem. The integral of z squared is 1/3 z cubed. 3/4 times 1/3 is 1/4. So 1/4 z cubed, which is being evaluated from 0 to 3. Notice I didn't write z equals 0 and z equals 3. It's our only variable left. If I insert 3 cubed is 27. 1/4 times 27 is 27/4. Minus, if I insert 0, I get 0, so that changes nothing, and then we're done. So it's pretty straightforward. And honestly, the order in which we integrated was completely irrelevant. So I invite you to try this problem again, but mix up the order. For example, maybe you want to do dy dz dx. Just make sure that whatever order your differentials are in, the limits of integration on the integrals correspond accordingly. For example, if we started with dy, then the first integral should be integrated from -1 to 2. But I invite you to try it in a different order, and you should come up with the same answer. In fact, there are 5 other orders you could put these in. All of them should be the same answer.